In the early universe, a black hole switched on before its galaxy even existed. That sounds impossible, but the James Webb Space Telescope just proved it true. 50 million times heavier than our Sun, this black hole sits inside a galaxy only 1,300 light-years wide, a sliver next to our own Milky Way. The black hole alone makes up 2 out of every 3 pounds of matter in the whole system. We will travel back 700 million years after the Big Bang, ride starlight bent by gravity itself, and meet a second monster black hole devouring its galaxy 5 times faster than physics should allow. If galaxies do not build black holes, something built galaxies around black holes instead. If this pulls you in, hit like and subscribe. More mysteries like this are coming. Now, let's go back to the beginning of everything. A single point of night sits at the centre of nearly every galaxy in the universe, including our own. Cross a certain line near it and there is no turning back, no return trip, ever. That line is called the event horizon, and it marks the place where gravity finally wins completely. Nothing inside can escape, not light, not radio waves, not even a scream. A black hole is not a hole in space the way a hole appears in a piece of paper. It is matter packed so tightly that its own gravity folds space around it, the same way a heavy bowling ball dropped onto a stretched blanket pulls the fabric into a deep well. Picture our Sun. More than 1 million Earths could fit inside it. Then picture crushing all of that mass down into a ball the size of a small city. That is close to the density many black holes reach, though some grow far heavier and stranger still. Most black holes form when a giant star burns through its fuel and collapses under its own weight, folding smaller and smaller until nothing can stop it. Stars many times heavier than our Sun end their lives this way, blasting their outer layers into space while the core keeps falling inward forever. Scientists call the surviving core a stellar mass black hole, and it usually weighs somewhere between 5 and a few dozen times the mass of our Sun. That is the small version of the story. Some black holes are not small at all. At the centre of nearly every large galaxy sits a supermassive black hole, and these giants can weigh millions or even billions of times more than our Sun. Our own galaxy, the Milky Way, holds one of these giants at its centre, a black hole named Sagittarius, a star. It sounds enormous by human standards, yet compared to the rest of the Milky Way, it barely counts as a rounding error. If the whole galaxy were the size of a football field, that giant black hole would be smaller than a single grain of sand resting at the 50-yard line. That size difference used to feel like a settled fact. One of the quiet rules the universe seemed to follow everywhere astronomers looked. Big galaxies build up first. Stars are born, live, and die inside them for millions of years. Only after all of that does a black hole slowly grow large enough to matter. It felt as solid as gravity itself, tested across thousands of galaxies close enough for telescopes to study clearly. Every one of them followed the same pattern, a small black hole tucked quietly inside a much larger galaxy, the same way an acorn sits small at the base of an oak tree already grown tall around it. That pattern held for decades. It held through every major discovery, every new telescope, every generation of astronomers trained to expect it. Then a new machine was lifted into space, built specifically to look further back in time than anything before it, and pointed toward galaxies so ancient their light left before Earth even had continents. What it found broke the pattern completely, and once you see what it found, the acorn and the oak tree stop making sense. A young universe begins simply, mostly hydrogen and helium drifting through the dark, cooling after the heat of the Big Bang. Slowly, gravity pulls these gas clouds together, clumping them into thick pockets that grow denser by the day. Inside those pockets, pressure builds until the gas ignites, and the first stars flicker on like matches struck in a pitch-black room. This is where galaxies are supposed to begin their lives, according to the textbook version of events. Gas comes first, stars come second, born in bright clusters that light up the surrounding cloud from within. Those stars live out their lives, some for millions of years, some for billions, burning steadily until they run out of fuel. The heaviest of them die in dramatic fashion, collapsing inward and sometimes leaving behind a small black hole as a kind of cosmic leftover. Over time, as more stars die and more matter falls inward, these small black holes merge and grow, one meal at a time, slowly climbing in mass across hundreds of millions of years. Only after a galaxy has had time to build a full population of stars does its central black hole reach a serious size, feeding on gas, dust, and the occasional unlucky star that wanders too close. This slow build-up matched every nearby galaxy astronomers had measured clearly, right up until they started looking further back in time than anyone had managed before. Picture baking bread. First you need the flour and water, then time for the dough to rise, and only at the very end does the loaf come out of the oven fully formed. Galaxies were thought to work the same way: ingredients first, structure slowly built over a long stretch of time, with the black hole as the very last piece to fully form. Under this model, a black hole should never appear before its galaxy has had time to grow up around it. It should never be the main event. It should always be the smaller, quieter partner riding along inside something much larger and much older. That expectation shaped how astronomers searched the sky and how they interpreted nearly everything they saw, because a model that has worked for every nearby galaxy earns a certain amount of trust. Scientists build entire careers testing ideas like this one, checking galaxy after galaxy, confirming the same pattern again and again until it stops feeling like a theory and starts feeling like a law. Confidence built on nearby galaxies, though, is confidence built on a narrow slice of time, since light takes time to travel, and everything close to Earth is also relatively recent in cosmic terms. To test whether this rule holds everywhere, astronomers needed to look far back in time, all the way to the earliest chapters of the universe, when the very first galaxies were only just beginning to take shape. That kind of light is faint, stretched thin, and buried under billions of years of cosmic dust. It would take an extraordinary telescope, one built specifically to catch light this old and this weak, to even attempt the search. Most astronomers expected that telescope to simply confirm the same steady recipe in sharper detail, just pushed a little further back in time. Once that telescope switched on, the flour and water model of galaxy building met something it was never designed to explain. Walk into any nearby galaxy, and the numbers barely change. Astronomers have measured hundreds of them: spirals, ellipticals, dwarfs, giants, and the ratio holds steady almost every single time. The central black hole makes up less than 1% of the galaxy's total mass, often far less. In our own Milky Way, Sagittarius A star weighs about 4 million times the mass of our Sun, which sounds like a staggering number until you place it beside the rest of the galaxy, home to hundreds of billions of stars. Picture a full stadium packed with 100,000 people, and somewhere inside that crowd stands a single person representing the black hole. That is roughly the scale of the imbalance, one small figure lost inside an enormous crowd. This tiny ratio was not a lucky coincidence found once and assumed to be universal. It showed up again and again in galaxy after galaxy, close enough for telescopes to measure with real precision. Scientists even gave it a name, the black hole to galaxy mass relation, and used it to predict how galaxies should behave long before they had the tools to check every corner of the sky directly. If you knew how bright a galaxy's stars were, you could make a solid guess at the size of the black hole buried at its heart, because the two numbers move together in lockstep, like a shadow that always matches the shape casting it. This relationship became one of the quiet pillars holding up the entire model of how galaxies grow. It suggested a kind of built-in feedback system, where a growing black hole eventually blasts out so much radiation that it slows down star formation nearby, keeping both the black hole and its galaxy in a rough kind of balance over billions of years. Neither one should ever run far ahead of the other. Astronomers checked this balance across galaxies of every size and shape, from small dwarf galaxies barely a tenth the size of the Milky Way to sprawling giants many times larger, and the ratio barely budged from one system to the next. The black hole should never dominate. It should always be the smaller partner, however massive it might sound on its own. That balance felt so dependable that when astronomers pointed new instruments at galaxies billions of light years away, they expected to find the same story playing out, just further back in time. A smaller, younger version of the same steady partnership, gas and stars leading the way while a modest black hole quietly grew in the background. Every rule needs a stress test though, and the biggest stress test available to astronomers is time itself, pushing a model back toward the very edge of the observable universe to see whether it still holds. Nobody expected to find a galaxy where that balance was not just tilted, but flipped completely upside down. A system where the black hole itself became almost the entire story, with barely anything left over to call a galaxy at all. Yet that is exactly what a new generation of telescopes would eventually uncover. Tucked inside some of the faintest, oldest light in the observable universe, hiding in plain sight until someone finally built an instrument sharp enough and patient enough to catch it. In the winter of 2022, a telescope orbiting nearly 1 million miles from Earth opened its golden mirror for the first time and began collecting light that had been travelling since almost the dawn of the universe. This was the James Webb Space Telescope, named after a former NASA administrator, built as the successor to the aging Hubble Space Telescope that had served astronomers for more than 3 decades. The new observatory did not simply ride into orbit around Earth the way Hubble did. It travelled nearly 1 million miles out to a stable gravitational parking spot scientists call the second Lagrange point, trailing behind Earth like a kite tied to a very long string, always shielded from the glare of the sun. Unlike Hubble, which mostly captured visible light, this new observatory was built to see in infrared, a kind of light invisible to human eyes, but essential for spotting the very oldest galaxies in the universe. Here is why that distinction matters so much. As the universe expands, light travelling toward us gets stretched out, shifted from visible wavelengths into infrared, the further back in time that light originated. A galaxy that shone brightly in visible light billions of years ago now reaches Earth as a faint whisper of infrared, invisible to older telescopes but perfectly readable to this new one. Picture stretching a rubber band with a pattern drawn on it. The pattern does not disappear, it simply spreads out, and only the right kind of eye can still read it clearly. The telescope carried a mirror built from 18 hexagonal gold-coated segments, unfolding piece by piece in space like a flower opening its petals, until it formed a surface more than 21 feet across, far larger than anything sent into space before it. Beneath that mirror hung a sun shield the size of a tennis court, folded like origami for launch and unfurled layer by layer once safely in space, keeping the telescope's sensitive instruments hundreds of degrees colder than the surface facing the sun. That size and that cold both mattered enormously, because a bigger, colder mirror gathers more light and loses less of it to its own heat, and more usable light means fainter, older objects finally become visible. The project spanned more than 2 decades of development and cost roughly $10 billion, built through a partnership between NASA, the European Space Agency, and the Canadian Space Agency, with engineers across more than a dozen countries contributing pieces to the final design. Its launch alone carried enormous risk, since more than 300 separate mechanisms needed to unfold correctly in space, one after another, with no astronaut able to fly out and fix a single one if something went wrong. Scientists had spent decades planning exactly what they hoped to find, with an instrument this powerful, galaxies from the earliest years after the Big Bang, the first generation of stars ever to ignite, maybe even hints about how the very first black holes came to exist. Nobody expected the telescope to start breaking the rules almost immediately, and nobody expected the very first hints of trouble to come from images that, at first glance, looked almost unremarkable, just a scattering of small, faint reddish points buried among thousands of ordinary galaxies in the telescope's very first deep-field pictures. Astronomers poring over those first deep-field images noticed the pattern almost by accident. Scattered across picture after picture sat tiny, intensely red points of light that did not match anything in the existing catalogues built from decades of Hubble observations. They were too small and too faint to be full galaxies in the traditional sense, yet too bright and too red for anything else scientists had catalogued before. At first, the explanation seemed simple enough. Some researchers assumed these were just distant, ordinary galaxies, their light stretched and reddened by the sheer distance involved, nothing more than an expected side effect of looking far back in time. That explanation held up for a while until the numbers stopped cooperating. These objects kept appearing in image after image, cluster after cluster, always compact, always deeply red, always sitting impossibly far back in cosmic history, in numbers far too high to write off as a rare coincidence. Within the telescope's very first full year of operation, astronomers had already catalogued dozens of them, then hundreds, scattered across nearly every deep field the telescope pointed at. A discovery this common could not simply be dismissed as a handful of unusual outliers. By the end of the telescope's second full year in operation, that count had climbed even higher, with these small red points showing up in nearly every deep field image the telescope pointed at, regardless of which patch of sky researchers chose to study. A discovery rate that high demanded a serious explanation rather than a shrug. It needed a name and needed serious follow-up study. The name that stuck was almost playful for something this unsettling little red dots, chosen simply because that is exactly what they looked like on screen, small, round and stubbornly crimson against the black backdrop of deep space. Early debate over what these objects actually were split the astronomical community into competing camps. Some argued for thick clouds of dust wrapped around ordinary young galaxies, blocking bluer light the way smoke blocks a lamp across a room. Others suspected something closer to a burst of newborn stars, so densely packed and so young that their light simply had not had time to spread out into a normal galactic shape yet. A smaller, more cautious group raised a stranger possibility from the very beginning, that the red glow and compact size pointed towards something actively feeding at the centre of each object, releasing energy the way material does when it spirals toward a black hole, rather than simply shining the way ordinary starlight does. Conference talks and hallway arguments over these three competing explanations became almost a running joke among astronomers working with the new telescope's data, since each new batch of images seemed to hand fresh ammunition to every side of the debate at once, and no single explanation managed to account for every strange detail on its own. Untangling which explanation was correct would require more than pictures alone. It would require breaking the light from these objects apart, wavelength by wavelength, searching for the specific fingerprints that only hot, fast-moving gas near a feeding black hole tends to leave behind. That deeper investigation was already underway, quietly, patiently, and what it revealed would turn a strange, catchy nickname into one of the biggest open questions in modern astronomy. Little red dots do not behave like any galaxy catalogued before the James Webb Space Telescope switched on. A normal young galaxy spreads its light out across a visible disk or a loose, glowing cluster of stars, something with structure, something with shape you could trace with your finger on a screen. These new objects refused to do that. Under the telescope's sharpest images, most little red dots stayed stubbornly compact, small and unresolved, barely more than a single glowing point, as if someone had taken an entire galaxy and squeezed it down into something the size of a city seen from an airplane window. As researchers gathered spectra, essentially breaking the light apart into its individual colours, the way a prism splits sunlight into a rainbow, patterns started emerging that pointed towards something active rather than passive. Many little red dots showed the telltale signature of hot, fast-moving gas, the exact kind of signature astronomers associate with material spiraling into a feeding black hole. That was the first solid hint that these were not simply small dusty galaxies minding their own business in the early universe. Something inside many of them was actively devouring matter, glowing fiercely as it did, the way a campfire flares brighter each time fresh fuel gets tossed onto it. Researchers found this same telltale gas signature repeated across a large share of the objects they studied closely, not just one or two isolated cases, which made the pattern far harder to dismiss as simple coincidence, an instrument quirk, or contamination hiding somewhere in the data. Stranger still, these objects turned out to be common, not a rare fluke spotted once and never again, but a whole population scattered across nearly every deep field image the telescope captured, hundreds of them found within just the first couple of years of observations. Yet just as quickly as they appeared, they seemed to vanish from the historical record. Search for little red dots in galaxies closer to our own time, less than about 1.5 billion years after the Big Bang, and they become almost impossible to find. Whatever these objects were, they seemed to exist only briefly, in a narrow window early in cosmic history, before either fading, transforming, or being swallowed into something larger, the way morning fog burns off completely once the sun climbs high enough. Astronomers were left holding a genuine mystery with almost no historical precedent to compare it against. A population of small, blazing red objects, likely powered by feeding black holes, thriving briefly in the universe's earliest years, and then disappearing almost entirely from every later chapter of cosmic history, as if an entire generation of cosmic monsters had lived fast, and then slipped quietly out of view. To understand what was really happening inside them, scientists needed more than pictures or even spectra taken in isolation. They needed a way to measure the mass hidden at the centre of one of these strange little points of light directly, with real precision rather than an educated guess. That would require an extraordinary rare stroke of cosmic luck, one specific little red dot happening to sit exactly behind the right kind of magnifying glass in the sky, at exactly the right angle for astronomers to finally see straight through to its very centre. Nearly 4 billion light-years from Earth sits a sprawling collection of hundreds of galaxies bound together by gravity, a structure astronomers named Able 2744. Its nickname carries a bit more flair, Pandora's Cluster, earned because of the astonishing variety of cosmic phenomena packed inside it: colliding galaxies, sprawling gas clouds stretched by past collisions, and enough combined mass to warp the fabric of space itself. That last detail turned out to matter more than anyone initially expected. Pandora's cluster contains so much mass, most of it invisible dark matter rather than the glowing galaxies themselves, that its gravity bends the space around it, the way a heavy stone dropped onto a trampoline bends the surface beneath it. Altogether, the cluster carries the combined mass of hundreds of individual galaxies, plus a far larger unseen halo of dark matter wrapped around all of them, making it one of the heaviest single structures astronomers have mapped in careful, painstaking detail anywhere across the observable sky. Anything behind that warp, viewed from Earth, gets its light bent and distorted on the way to us, sometimes stretched into arcs, sometimes duplicated into multiple copies of the same distant object scattered across the sky. Astronomers had studied Pandora's cluster for years, mapping its warping effect in careful detail, because that distortion turns out to be enormously useful. It works like a natural magnifying glass, one built by gravity itself rather than glass and metal, capable of brightening and enlarging anything unlucky, or lucky, enough to sit directly behind it. Objects too faint and too distant for even the most powerful telescope to see clearly can sometimes become visible only because a massive cluster like this one happens to sit precisely in the way, bending and boosting their light before it ever reaches Earth. When astronomers pointed the James Webb Space Telescope toward Pandora's cluster, they were not simply photographing the cluster itself. They were using it as a tool, a cosmic telescope built from warped space, to peer even further into the deep universe hiding directly behind it. Buried in that boosted, bent light, researchers spotted one of the little red dots first catalogued only a few years earlier, an object that would eventually be named Able 2744 or QS01, or simply QS01 for short. On its own, without the cluster's help, QS01 would likely have been far too faint to study in any real detail, just another dim red smudge lost among thousands of others scattered across the deep field images, the kind of object that gets logged in a catalogue and then quietly set aside for lack of any usable, detailed data to actually study. With Pandora's cluster sitting directly in front of it, everything about that faint red smudge was about to change, though not in the simple way anyone expected. Gravity, unlike an ordinary lens on a camera, does not politely brighten a single clean copy of a distant object and simply leave it at that. Depending on exact alignment, it can bend the same beam of light along more than one path at once, sending each version toward Earth from a slightly different angle, arriving as what looks, at first glance, like several separate objects sitting close together in the sky, rather than the single distant source that actually produced all of them. Gravity does not just pull objects together, it also bends the path that light itself travels through space. Albert Einstein predicted this strange effect more than a century ago, describing gravity not as a simple force reaching out and grabbing things, but as a curve carved into space itself by anything with enough mass. Picture a bowling ball resting on a stretched sheet of rubber, sinking down and pulling the fabric into a deep curved well around it. Now roll a marble across that sheet from far away. It does not travel in a straight line anymore. It curves around the well, following the shape the bowling ball carved into the surface. Swap the marble for a beam of ancient starlight, and the bowling ball for an entire cluster of galaxies, and the same basic bending still happens, just on a scale that stretches across billions of light years, rather than a few feet of rubber sheeting stretched over a table. Light behaves the same way when it passes near something massive enough, a star, a galaxy, or an entire cluster of galaxies bound together by gravity. This bending effect is called gravitational lensing, and it turns massive objects in space into something close to enormous, imperfect magnifying glasses. The effect grows stronger with more mass, and few things in the universe carry more mass, packed into one place, than an entire cluster of galaxies like Pandora's cluster, where hundreds of individual galaxies orbit a shared, invisible center of gravity built mostly from dark matter. When light from a much more distant object, in this case the faint red glow of QS01, happens to pass close to a massive cluster on its long journey to Earth, that light gets bent, stretched, and sometimes split apart entirely. The result depends heavily on exact alignment, almost like trying to look through a specific, imperfect patch on an old window pane. Shift your head slightly and the view distorts differently, sometimes stretching an image into a long curved arc, sometimes duplicating it into 2 or 3 separate copies scattered nearby, each one carrying its own slightly different version of the same underlying light. Astronomers rely on this effect constantly, treating massive clusters as natural telescopes stacked directly in front of their instruments in space, adding extra magnifying power that no telescope built by human hands could ever achieve alone, no matter how large its mirror. Without gravitational lensing, some of the faintest, most distant objects in the universe would simply never appear bright enough to study in any real detail, no matter how long a telescope stared at that patch of sky, no matter how large its mirror or how many hours of exposure time astronomers were willing to spend. With it, previously invisible objects suddenly snap into focus, their light concentrated and amplified by the warped space of the cluster sitting between them and Earth. Every lensed object tells astronomers 2 separate things at once: what the object itself actually looks like, and how the specific geometry of the cluster in front of it happened to bend and multiply that light on the long journey here. For QS01, both of those details were about to become unusually important, because the exact way its ancient light had been bent and reshaped was about to hand astronomers something far rarer than a simple brightness boost. When the team finally measured exactly what Pandora's cluster had done to QS01's light, the results went far beyond a simple brightness boost, revealing a rare double effect layered onto one single faint target from the dawn of the universe. The cluster's gravity had split the object's light into 3 separate images, 3 versions of the very same ancient point of light, scattered across different spots in the sky, each one arriving along a slightly different bent path carved through the cluster's warped space. On top of that split, the cluster magnified the object dramatically, boosting QS01's brightness by nearly 100 times compared to how it would have appeared without any lensing at all. Astronomers rarely encounter both effects layered together this cleanly on a single object, from this deep in cosmic history, a splitting and a brightening happening at once on the exact same faint target. Stack those 2 effects together and something rare had happened. A single, faint red smudge from the dawn of the universe had been turned into 3 separate, dramatically brightened copies of itself, each one a fresh opportunity to study details that would otherwise have stayed hopelessly buried in noise. For astronomers, this was closer to a gift than an accident. A single distant little red dot suddenly offered 3 separate viewing angles, 3 chances to gather data, 3 independent checks against each other to confirm that whatever they measured was real and not some kind of instrument error or fluke. Picture taking the exact same photograph through 3 different cameras, positioned at 3 different angles, all pointed at the same distant subject at once. If all 3 come back showing the same fine detail, that detail becomes far more trustworthy than any single shot ever could on its own. That is roughly what the triple image of QS01 offered the research team, a built-in way to cross-check their own results before ever publishing anything. Without that near 100-fold magnification, QS01 would have stayed a barely visible smudge, its finer details buried far below what even the James Webb Space Telescope could resolve on its own from that staggering distance. With it, the object suddenly became bright enough and sharp enough for a much more ambitious kind of measurement, one that had never before been attempted with this level of confidence on an object from this deep in cosmic history. Earlier surveys of distant black holes had always relied on indirect methods, estimating mass from overall brightness, or from rough statistical models borrowed from closer, better understood galaxies. QS01's triple, magnified image offered something else entirely, a genuine chance to look directly at the motion of gas swirling near the object's very centre, rather than simply guessing at what might be hiding there. That kind of direct measurement had remained mostly out of reach for objects this far back in time, blocked not by a lack of scientific ambition, but by a simple lack of light. Pandora's cluster had just solved that problem, handing researchers exactly the kind of boosted, tripled signal needed to finally attempt it, a problem years of careful planning and telescope time alone could never have solved without a lucky cosmic assist sitting directly in the way. QS01 sits so far away that its light left home when the universe itself was barely a child. Astronomers measure that distance not in miles or light years alone, but in time, describing how long ago the light we now see actually departed its source. In this case, the light reaching Earth's telescopes left QS01 roughly 700 million years after the Big Bang, meaning we're not looking at what that object looks like today, we are looking at a snapshot frozen from deep in the universe's early childhood, a fossil beam of light rather than a live broadcast. For comparison, the universe today is nearly 14 billion years old, which means QS01's light has been travelling steadily toward us for well over 90% of all of cosmic history, crossing a gulf of space and time almost too vast to picture in any everyday terms. 700 million years sounds like an enormous stretch of time on its own, and in a human sense, it is almost impossible to hold in your head. Yet on a cosmic timeline, it represents an early, formative chapter, closer to the opening pages of the universe's story than anywhere near the middle. The very first stars were only just beginning to light up the darkness in large numbers, The first galaxies were still stitching themselves together out of gas and gravity. This was an era astronomers sometimes call cosmic dawn, the period when the universe's fog of neutral hydrogen finally began clearing, lit from within by the earliest generations of stars and galaxies switching on for the first time, one small pocket of light at a time, spreading slowly across the darkness like scattered porch lights turning on across a sleeping town. Finding any structured object this far back is already remarkable. Finding one bright enough, and fortunately magnified enough, to study in real detail borders on extraordinary luck. Most objects from this era remain frustratingly faint and blurry, offering astronomers only rough estimates rather than precise measurements, smudges rather than genuine data, forcing scientists to lean on statistics and averages instead of a single, confident number for any one object. QS01, tripled and boosted nearly 100 times by the gravitational lens sitting in front of it, offered something rarer, a genuine opportunity to look closely, to measure precisely, rather than simply guess from a smudge of light. Researchers wasted no time turning the full power of the James Webb Space Telescope toward this rare opportunity. They were not just interested in confirming that QS01 existed, or roughly how far away it sat. They wanted to understand what exactly was inside it, what was producing that intense, telltale red glow that first caught their attention among thousands of little red dots scattered across the deep field images. Was it simply dust? Thick clouds blocking bluer light the way smoke blocks a lamp on the other side of a room? Was it a burst of newborn stars blazing brightly enough to redden an entire small galaxy? Or was it something else entirely? Something closer to the centre? Something feeding rather than simply shining? To answer that question definitively, astronomers needed to measure motion itself, tracking exactly how fast material was moving inside this tiny, ancient point of light. A photograph tells you what something looks like from the outside. A spectrum tells you what something is actually doing on the inside. Hidden details a picture alone could never reveal. To understand QS01 in real, precise detail, astronomers turned to an instrument aboard the James Webb Space Telescope called the Near-Infrared Spectrograph, a device built specifically to take incoming light and split it apart into its individual wavelengths, the same basic idea as a prism splitting ordinary sunlight into a rainbow, except far more precise and tuned specifically to infrared light. Every wavelength inside that split-apart rainbow carries information. Certain colours brighten or dim depending on what elements are present, how hot the material is, and crucially how fast it happens to be moving toward or away from Earth. That last detail comes from a phenomenon called the Doppler effect, the same basic principle behind an ambulance siren sounding higher pitched as it races toward you and lower pitched as it speeds away. Light works similarly. Material moving toward Earth has its light squeezed toward bluer wavelengths, while material moving away gets stretched toward redder wavelengths. By carefully mapping these tiny shifts across QS01's spectrum, researchers could reconstruct something remarkable, an actual motion map, tracing how gas was moving in different regions surrounding the object's centre, region by region, rather than settling for one single blended reading averaged across the whole system. This was not a simple, one-time measurement taken and filed away. The team used a specialised mode of the instrument capable of capturing spectra across many individual points simultaneously, essentially building a detailed velocity map rather than settling for a single averaged reading pulled from the whole object at once. Picture standing above a spinning carousel, timing exactly how fast horses move on the near side compared to the far side, then using those numbers to calculate how fast the whole carousel is actually turning. Astronomers applied a similar logic to gas swirling around the heart of QS01, tracking material on one side appearing to move toward Earth, while material on the opposite side appeared to move away. What they found was a pattern too clean, too orderly, to be random turbulence or chaotic outflowing gas blasted away from an exploding star. The motion traced a smooth, consistent rotation, gas circling a central point in an organised, predictable pattern, The unmistakable signature of something with real gravitational authority sitting at the very centre. This kind of clean, orderly motion rarely shows up by accident in astrophysics. Chaotic gas clouds, colliding galaxies, and violent stellar explosions tend to produce messy, scattered velocity readings, not smooth, symmetric rotation. What the team was staring at looked instead like something obeying a very old, very familiar set of rules, the same basic rules that keep planets orbiting steadily around our own sun rather than drifting off in random directions or spiralling away into empty space. Confirming that connection would require comparing the motion directly against a well-established mathematical pattern, one first worked out centuries ago by an astronomer studying the movement of planets rather than distant galaxies, a pattern that has never once failed a real test since. 4 centuries ago, an astronomer named Johannes Kepler worked out a careful set of rules describing exactly how planets move around the Sun, rules so precise and so reliable that they still hold up perfectly under modern testing today. Planets closer to the Sun move faster, tugged along by stronger gravity at close range. Planets farther away move slower, drifting through their much longer, lazier orbits. The whole system traces smooth, predictable orbits, governed entirely by the Sun's gravity sitting steady at the centre. Astronomers call this pattern Keplerian motion, and it shows up anywhere a massive central object dominates the movement of everything orbiting around it, whether that object is a star, a planet, or something far stranger. When researchers compared the velocity map traced inside QS01 against this centuries-old pattern, the match was almost startling in its precision and consistency across every part of the object. Gas near the centre moved rapidly, gas farther out moved more slowly, exactly the relationship Kepler had described for planets orbiting our Sun, just scaled up to a size and intensity almost impossible to picture. This was not gas swirling chaotically after a violent collision between 2 galaxies. It was not material blasted outward by an exploding star, scattering randomly in every direction like debris from a firework. It was orderly, predictable, disciplined motion, the kind that only appears when nearly all of the system's mass sits concentrated in one small central point, exerting its gravitational pull evenly in every direction. Team co-leader Ignace Geortzbalis of Cambridge University later explained why this particular detail mattered so much, noting that this clean, orbital signature confirmed most of the mass inside QS01 was not spread evenly across some wide glowing disk of stars. It was packed into the very centre, concentrated tightly enough to command the motion of everything swirling around it. Once astronomers had confirmed the shape of the orbit, the next step became almost a straightforward calculation, the same basic math used for centuries to weigh the Sun using nothing more than the orbital motion of the planet circling it. If you know how fast material is moving at a certain distance from the centre, and you know that distance itself, you can calculate exactly how much mass must be sitting there to hold everything in that particular orbit through gravity alone. Apply too little mass to the equation, and the fast-moving gas near the centre would simply fly outward, escaping the system entirely rather than staying trapped in a tight, stable loop. Apply too much, and the orbits would look completely different, tighter, faster, distorted in ways that did not match what the telescope had actually recorded. The equation left almost no room for guesswork or wishful thinking, since only one precise number could make every observed data point line up correctly at once. Only one specific mass, plugged carefully into the equation, produced an orbit matching the real data gathered from QS01 spectrum with genuine precision, checked and rechecked across all 3 lensed images before anyone trusted it. When the team finished the calculation, the number that emerged was staggering, especially for an object this young, this early, this deep in the universe's formative years. 50 million. That was the number astronomers finally landed on. 50 million times the mass of our Sun, packed into a single black hole sitting at the exact, unmistakable centre of QS01. Say that number slowly out loud, and it still barely lands, so picture it differently instead. Our Sun alone already outweighs Earth by more than 300,000 times, easily swallowing every planet, moon and asteroid in our solar system, combined without even noticing the difference. Now imagine 50 million suns, compressed down, folded into a single point smaller than a solar system. All of that mass locked inside one black hole's crushing grip, a weight so concentrated that nothing caught nearby ever finds its way back out again. This was not a modest, ordinary black hole quietly sitting inside a young forming galaxy. This was a genuine heavyweight, comparable in scale to some of the largest black holes ever measured anywhere in the observable universe, yet somehow already fully formed at a moment when the universe itself had only just celebrated its 700 millionth birthday, barely 5% of its current age today. Discovering a black hole this massive was remarkable enough on its own, a genuine milestone for any telescope to capture this deep in cosmic history. What made the measurement genuinely historic was how it had been obtained. Nearly every black hole mass previously measured at similarly extreme distances had been estimated indirectly, inferred from brightness, from rough models, from educated guesswork built on assumptions borrowed from closer, better studied galaxies. QS01 offered something far rarer, a direct measurement built from actual observed motion, actual gas tracked in actual orbit around the object itself. Roberto Maiolino, another member of the Cambridge-led research team, later described the discovery as a genuine paradigm shift, a total revisiting of the classical scenarios describing how black holes form and grow in the first place. That kind of language rarely appears casually in a field built on careful, cautious statements. Scientists tend to speak in probabilities, in margins of error, in phrases carefully hedged against overstatement. Calling something a paradigm shift means the existing rulebook no longer adequately explains what the data shows. For decades, the assumption had been simple, even elegant. Black holes start small, born from the collapsed core of a single massive star, then slowly grow larger over hundreds of millions of years, feeding gradually on surrounding gas and the occasional unlucky star pulled too close. Under that model, a 50 million solar mass black hole should take an enormous stretch of cosmic time to build. Patiently, meal by meal, star by star, across a timeline stretching comfortably beyond 1 billion years, QS01 had somehow reached that mass while the universe itself was barely more than 5% of its current age. Either something had fed this black hole at a shockingly accelerated pace, defying the normal physical limits astronomers had assumed governed black hole growth, or the black hole had never really started small in the first place. Both possibilities sounded almost equally strange and equally difficult to explain using the old, comfortable rulebook everyone had trusted for so long, and the next measurement was about to make choosing between them even harder. Every galaxy needs room to hold its stars, its gas, its dust, and everything else orbiting within it. QS01 barely offered any room at all, cramming an extraordinary amount of mass into an almost impossibly small footprint. When astronomers measured the full extent of the object, the entire structure, not just the black hole itself but the galaxy wrapped around it, they found something spanning roughly 1,300 light-years across. That number needs real context to land properly, because on its own it can sound almost impressively large. It is not by the standards astronomers actually use when measuring galaxies. Our own Milky Way stretches across roughly 100,000 light-years from one edge to the other, meaning the entire structure surrounding QS01's black hole could fit inside our galaxy nearly 80 times over, tucked comfortably within a single spiral arm with plenty of room left to spare. Picture the difference between a small neighbourhood park and an entire national forest stretching for hundreds of miles, and you start to grasp the scale mismatch hiding inside this discovery. Even a modest nearby galaxy, nothing close to the size of the Milky Way, would typically span tens of thousands of light-years, dwarfing QS01's entire structure many times over. This was not a modest-sized galaxy, hosting an unusually large black hole somewhere near its core. This was something closer to the opposite, an almost impossibly compact structure, barely larger than a dense star cluster, built around a black hole that, by every previous rule astronomers had trusted, should require a galaxy dramatically larger to support it. Normal galaxy formation models simply did not produce objects this small containing black holes, this massive, not at any stage, not at any point in cosmic history previously studied in careful detail, no matter how researchers adjusted the assumptions feeding into those models. Something about QS01 broke the expected relationship between a black hole's size and the size of the structure meant to contain it, and the mismatch was not subtle. It was not a 10% deviation easily explained away by measurement error or unusual viewing angles. It was a difference vast enough to make astronomers double-check their instruments, rerun their calculations, and confirm the result from multiple independent angles, including all three of QS01's lensed images separately, before trusting the number enough to publish it. Every check came back the same. QS01 truly was this small, and its black hole truly was this massive, sitting together in a combination that should not have been physically possible, according to everything astronomers thought they understood about how galaxies and their central black holes grow together over time. This left researchers facing an uncomfortable, genuinely strange possibility, one that felt almost backward compared to everything the field had assumed for decades. Rather than a galaxy slowly building itself up over hundreds of millions of years, eventually growing large enough to nurture a serious black hole at its heart, QS01 looked more like a black hole that had simply arrived first, dominating a space barely large enough to contain it, with only a thin, faint wrapping of galaxy material left clinging around its edges, and the next measurement would confirm exactly how little galaxy was actually left. Here is where the numbers stopped simply being surprising and started genuinely rewriting the rulebook astronomers had trusted for decades. Astronomers calculated exactly how much of QS01's total mass belonged to the black hole itself, compared to everything else. All the gas, all the dust, any stars scattered throughout the surrounding structure. In a typical mature galaxy today, that ratio sits comfortably below 1%, sometimes far below it. A small, quiet passenger riding along inside something vastly larger, rarely noticed unless astronomers go looking for it specifically. QS01 flipped that ratio almost completely upside down. The black hole alone accounted for at least 2 out of every 3 units of mass in the entire system, meaning everything else combined, all the gas, all the dust, any stars present, made up less than a third of the total. Picture a school bus carrying 60 passengers, and imagine that just 2 of those seats hold literally everything else in the entire vehicle combined. Every bag, every backpack, every piece of equipment stored on board, while the other 58 seats are filled entirely by a single, enormous rider stretched heavily across them. That is roughly the imbalance astronomers found staring back at them from QS01's data, an imbalance so extreme it barely resembled a galaxy at all. This was not a galaxy with an oversized black hole tucked somewhere near its centre, a strange but explainable outlier. This was, for all practical purposes, a black hole first, wearing only the thinnest possible wrapping of galaxy material draped loosely around it. Researchers on the team put it plainly in their published findings, describing QS01 as barely a galaxy at all in the traditional sense, closer instead to a black hole, with only a small thin cloud of leftover gas still clinging nearby for company. That description matters enormously because it flips the entire assumed order of cosmic construction on its head. Every previous model assumed galaxies build the framework first, then slowly grow a black hole to match. QS01 looked instead like the framework barely existed, dwarfed almost entirely by the very thing it was supposedly meant to contain and support. This kind of imbalance had never been measured this cleanly before, not with this level of direct orbit-based precision, checked and confirmed across 3 separate lensed images of the very same distant object. Earlier hints of unusually large black holes in early galaxies existed scattered throughout the research literature, but most relied on indirect estimates, rough guesses built from brightness and modelling assumptions rather than confirmed measured motion. QS01 offered rare, hard proof, gas caught in genuine orbital motion, mass calculated directly from real physics rather than inferred through educated guesswork layered on top of assumption. Once confirmed, the 2/3 figure became difficult for the scientific community to dismiss or explain away as some kind of measurement fluke, an unusual viewing angle, or a quirk specific to only this one-lensed object. Something about the earliest black holes in the universe's history did not follow the same growth pattern astronomers had confidently mapped out across galaxies closer to our own time, and comparing QS01 directly against the one galaxy every viewer already knows would make that difference impossible to ignore. Bring the comparison home, back to our own galaxy, the one every single viewer already calls home, and the difference becomes almost impossible to overstate. Sagittarius A star, the supermassive black hole anchoring the centre of the Milky Way, weighs around 4 million times the mass of our Sun. That number alone sounds enormous, and by any everyday human measure it absolutely is. Yet set against the rest of the Milky Way, home to somewhere between 100 billion and 400 billion individual stars, spread across a wide disk roughly 100,000 light-years from edge to edge, that black hole barely registers at all. It accounts for a tiny fraction of the galaxy's total mass, quietly anchoring the centre while trillions of tons of gas, dust and stars orbit peacefully around it, mostly unaffected by its presence beyond simple gravitational pull, the same way a single anchor barely disturbs the wide harbour stretching out around it. Our own Sun itself sits roughly 26,000 light-years away from Sagittarius A star, safely distant, orbiting the galactic centre once every couple 100 million years without ever coming close enough to notice any real danger at all. The Milky Way, in other words, looks exactly like the textbook expected. A vast, sprawling structure with a modest, well-behaved black hole tucked quietly at its heart, doing its job without dominating the neighbourhood around it. Exactly the calm, orderly relationship astronomers had come to expect from every nearby galaxy studied so far. QS01 offers almost a mirror opposite picture entirely. Instead of a small black hole anchoring a vast galaxy, QS01 presents an enormous black hole barely wrapped in any galaxy at all, the relationship completely inverted from everything astronomers observe close to home. If you shrank the Milky Way down to match QS01's proportions, keeping the same ratio of black hole to galaxy, Sagittarius A star would need to weigh not 4 million solar masses, but hundreds of millions, an almost unimaginable jump, while the rest of the galaxy's visible structure would need to shrink dramatically to match, collapsing from a sprawling spiral down to something barely larger than a single dense star cluster, its spiral arms gone entirely. No galaxy anywhere near our own corner of the universe looks anything like that. This stark contrast tells astronomers something important about timing, about which came first in the earliest years of cosmic history. Our own galaxy likely followed something closer to the traditional path, gas and stars accumulating steadily over billions of years, with Sagittarius A star growing gradually alongside that slow build-up, never truly overtaking the structure surrounding it. QS01 appears to represent something else entirely, a different starting point, a different sequence of events, one where the black hole itself may have arrived first, fully formed and already dominant, before the galaxy around it had any real chance to catch up. That distinction raises an uncomfortable question for anyone who assumed our own galaxy's gentle, balanced relationship between star and black hole represented some kind of universal rule, one that a growing pile of new evidence was about to challenge even further. If a black hole this massive could not have grown gradually, feeding star by star across hundreds of millions of patient years, then something else entirely must explain how it reached 50 million solar masses while the universe was still practically a newborn. Researchers on the team began exploring an idea that sounded almost like science fiction. Only a decade earlier, the possibility that some black holes are born big, skipping the slow, patient build-up entirely. Under the traditional model, a black hole starts small, as what astronomers call a light seed, the collapsed remains of a single massive star, typically weighing somewhere between 10 and 100 times the mass of our Sun, barely a speck by supermassive standards. From there, growth happens gradually, feeding on nearby gas and merging with smaller black holes over vast stretches of time. Reaching 50 million solar masses from a starting point that small in less than 700 million years would require feeding at rates pushing far beyond what physics normally allows, gulping down matter faster and more continuously than nearly any known black hole has ever been observed doing, without a single significant pause along the way. An alternative idea offers a very different starting point entirely. Rather than beginning small and growing gradually, some black holes may form directly from the collapse of an enormous pristine cloud of gas, skipping the star formation step altogether. Picture a massive cloud of hydrogen and helium, far larger and far denser than anything ever needed to form an ordinary star, collapsing inward under its own gravity so quickly and so completely that instead of igniting into a bright glowing star, it plunges straight past that stage entirely, folding directly into a black hole from the very start. The way a sandcastle collapses all at once under its own weight, rather than washing away slowly, grain by grain, tide after tide. Under this scenario, sometimes called the direct collapse model, a black hole could begin its life already weighing tens of thousands, or even hundreds of thousands, of times the mass of our Sun, a massive seed rather than a light one, needing far less additional growth to eventually reach the kind of mass measured inside QS01. This idea had circulated in theoretical physics for years, discussed quietly in papers and conference presentations, but had remained largely untested, lacking any solid observational evidence to confirm it actually happened anywhere in the real universe rather than only on paper. QS01 offered something closer to a real-world test case, an object whose properties lined up suspiciously well with what a direct collapse black hole might look like in its earlier stages, a young, massive black hole barely wrapped in galaxy material, exactly the kind of leftover signature this theoretical process might produce. Confirming this idea definitively would require more than a single example though, no matter how compelling that example appeared. Scientists needed to know whether QS01 represented a rare, almost freakish exception, one strange object slipping through the normal rules by pure cosmic accident, or whether it represented something far more unsettling, an early glimpse into a pattern repeating quietly across the early universe, waiting patiently for astronomers to find the next one hiding somewhere in the dark. Astronomers have a specific word for anything on the periodic table heavier than hydrogen and helium, and it might sound strange coming from a group of scientists. They call it metal. Even elements like oxygen, carbon and nitrogen, anything forged inside a star rather than present since the very beginning of the universe. When researchers examined the light coming from the gas swirling around QS01, they searched carefully for the telltale fingerprints of these heavier elements, the same way a detective checks a room for fingerprints left behind by anyone who passed through it recently. What they found was almost nothing. The gas surrounding QS01 turned out to be almost purely hydrogen and helium, the two simplest elements in existence, with barely a trace of anything heavier mixed in anywhere. That detail might sound like a minor chemistry footnote, but to an astronomer, it reads like a smoking gun. Every heavier element in the universe, every atom of carbon in your body, every trace of iron, every grain of oxygen you breathe, was forged inside the nuclear furnace of a star and then scattered into space when that star eventually died, usually in a dramatic explosion called a supernova. Generations of stars living and dying seed the surrounding gas with these heavier elements over time, gradually enriching the cosmic environment the way compost slowly enriches plain soil, batch after batch, season after season over many years. A gas cloud rich in heavy elements has clearly been through several such cycles already, cooked and recooked by wave after wave of stars living out their lives and dying in turn. A gas cloud almost entirely free of them tells a very different story, one closer to raw, untouched material, barely altered since the earliest moments after the Big Bang itself. Picture opening a brand new box of crayons compared to a box that has clearly been used for years, worn down, mixed up, and covered in shavings from constant use. QSO-1's surrounding gas looked like that first box, fresh and essentially unused, exactly what astronomers would expect to find if star formation had barely gotten started in that particular pocket of space. This chemical purity fit almost perfectly with everything else the telescope had already revealed about QSO-1, an object dominated by an enormous black hole, yet strangely lacking the layered chemical fingerprint that generations of dying stars usually leave scattered behind them. If stars had been forming and dying in large numbers around this black hole for any meaningful stretch of time, the surrounding gas should show at least some trace of that history, some scattering of heavier elements mixed into the plain hydrogen and helium. Instead, the gas looked almost newly made, barely touched, sitting right beside a black hole already carrying 50 million times the mass of the Sun. Astronomers double-checked this chemical reading carefully, since a result this unusual demanded real scrutiny before anyone trusted it enough to build a bigger argument on top of it. The spectrum came back consistent across repeated checks, the hydrogen and helium signals strong and clear, any heavier element signal buried so deep in the noise it barely registered above the background at all. That combination, a chemically pristine environment wrapped directly around an already massive, fully formed black hole, would turn out to carry a far bigger implication than a simple chemistry result buried quietly in a research paper. Put the pieces together, and an uncomfortable picture starts to form. A black hole weighing 50 million times the mass of the Sun sits at the centre of QSO-1, fully formed, fully massive, already dominating its immediate surroundings completely. Around it, the gas remains almost chemically untouched, carrying barely any trace of the heavier elements that generations of dying stars normally leave behind them. Both of those facts point toward the exact same uncomfortable conclusion. Very few stars, if any meaningful number at all, had actually formed inside this system by the time astronomers captured its light, 700 million years after the Big Bang. That detail flips the expected order of events almost completely on its head. Under the traditional model, stars are supposed to arrive first, sometimes by the millions, burning and dying across hundreds of millions of years before a serious black hole ever gets the chance to grow at the centre. QSO-1 looked instead like a system where the black hole had somehow claimed its dominant position before that stellar factory had ever really switched on in earnest. Picture building an entire city around a single enormous skyscraper, one finished and towering before a single house, road, or shop had been built anywhere nearby it. That is roughly the sequence astronomers found themselves staring at. A black hole standing fully formed in an almost empty landscape, waiting patiently for the rest of the neighbourhood to catch up around it eventually. This detail mattered enormously for narrowing down exactly how QSO-1's black hole could have formed in the first place. If a long stretch of star formation had already taken place, feeding the black hole slowly through countless stellar deaths and mergers stretched across time, the surrounding gas should carry clear evidence of that history baked directly into its chemistry. It did not. The near-total absence of heavier elements strongly favoured the idea that this black hole had reached its enormous size through some other, far more direct pathway, one that skipped the long, patient build-up of star formation almost entirely from the very start. That pathway, the direct collapse of a massive, pristine gas cloud straight into a black hole without ever passing through a normal stellar life cycle first, suddenly looked less like a wild theoretical possibility and more like the most reasonable explanation left standing on the table. Confirming that idea beyond any real doubt would still require finding the same pattern repeated across other similar objects elsewhere in the sky, since a single case, however striking on its own, always leaves room for coincidence or an unusual set of circumstances unique only to this one particular system. Most ordinary galaxies studied closer to our own cosmic neighbourhood carry a thick, layered history of star formation written directly into their chemistry, generation after generation of stars leaving their fingerprints behind in the surrounding gas long before any astronomer ever points a telescope their way. QS01 carried almost none of that layered history, a system that looked, chemically speaking, closer to a newborn than to anything with a long, patient past stretching behind it across countless generations of stars. What QS01 had already done, though, was force astronomers to confront a genuinely uncomfortable question they had rarely needed to ask before, one with no easy answer waiting inside any existing textbook. Which comes first, the black hole or the galaxy? That question sounds almost childishly simple, the kind of thing a curious kid might blurt out during a museum tour, yet it had rarely needed serious consideration before QS01 forced the issue into the open. For decades, the answer felt obvious enough that nobody bothered writing it down as a genuine open question worth debating. Galaxies build up first, slowly, over hundreds of millions of years, gathering gas, igniting stars, and gradually assembling enough structure to eventually support and feed a serious black hole at the centre. The black hole was always assumed to be a product of the galaxy, something that emerges only after enough of the surrounding material has already organised itself into a functioning stellar system. QS01 suggested a genuinely different possibility, one that inverts that entire relationship almost completely. What if, at least sometimes, the black hole comes first, forming directly and rapidly from a collapsing cloud of primordial gas, with the surrounding galaxy only beginning to take shape afterward, gathering slowly around a black hole that had already claimed the centre long before any stars ever arrived. Under that scenario, a black hole would not be a late-stage product of galaxy growth at all. It would be closer to a seed, planted early, around which a galaxy might eventually grow, the same way a single tree planted first in an otherwise empty field can shape the entire layout of a park built up slowly around it over the following decades. Deciding between these two competing pictures carries real, lasting weight for understanding how the universe actually assembled its earlier structures in the first place, long before anything resembling a modern galaxy existed anywhere. If galaxies always come first, then black holes like the one inside QS01 should be vanishingly rare exceptions, unusual accidents produced only under highly specific and unlikely conditions rarely repeated elsewhere. If black holes can sometimes come first instead, then the standard model of galaxy formation, the one taught in classrooms and printed in textbooks for decades, would need a genuine rewrite, at least for describing conditions in the universe's earliest years. Neither possibility can simply be assumed true based on a single striking example, however dramatic that example looks laid out on paper. Confirming a real shift in scientific understanding always requires more than one data point, more than one object caught in a fortunate alignment behind a lucky gravitational lens somewhere in the sky. Answering that question properly would mean setting aside personal preference entirely, since plenty of astronomers found the black hole first possibility genuinely uncomfortable to accept, no matter how cleanly the data seemed to point that direction. Good science does not get to choose the tidier, more familiar answer, simply because it feels safer or more comfortable to believe, however tempting that shortcut might feel after decades of building a career on the older picture. Astronomers needed to know whether QS01 was a genuine outlier, a strange accident produced by some unusual local condition unlikely to repeat, or whether it represented the visible tip of something far larger, a pattern of black hole, first construction, quietly playing out across many corners of the early universe, waiting patiently for the right telescope, the right lens, and the right moment of luck. To understand exactly why scientists had trusted the old model for so long, it helps to look closely at how a black hole is actually thought to form from a dying star in the first place. A massive star, many times heavier than our Sun, spends most of its life locked in a careful balancing act, nuclear fusion in its core pushing outward with tremendous force, while its own gravity pulls just as hard in the opposite direction, squeezing everything steadily inward. For millions of years, these two forces stay locked in a rough standoff, keeping the star stable and steadily shining bright in the darkness. Eventually, the star runs out of the lighter fuel needed to keep that fusion reaction burning strong and steady. Without enough outward pressure left to resist gravity, the core begins to collapse, falling inward on itself in a matter of seconds, a process that took millions of years to properly set up and only moments to finish completely. For the heavier stars, nothing can stop that collapse once it truly begins in earnest. The outer layers of the star often get blasted outward in a brilliant explosion called a supernova, briefly outshining an entire galaxy of ordinary stars combined, while the crushed, collapsed core left behind keeps falling inward, past every stage that might have stopped a lighter star, all the way down into a genuine black hole. This entire sequence, birth, life, collapse, explosion, and finally a newborn black hole left behind, typically takes millions of years to fully play out from start to finish, even before that fresh black hole has grown large enough to matter much on any cosmic scale. Multiply that timeline across the countless generations of stars needed to feed and grow a black hole all the way up to millions or billions of solar masses, and the total process stretches out across hundreds of millions, sometimes billions, of years altogether. That long, patient timeline is exactly why astronomers had always assumed black holes needed a fully developed galaxy around them first, providing a steady, reliable supply of dying stars to slowly build up mass over an enormous stretch of cosmic time. Skip that step entirely, and the timeline for building a 50 million solar mass black hole collapses down dramatically, from something requiring the better part of 1 billion years down, to something that could, in theory, happen almost immediately, within the very first chapters of the universe's existence. That shortcut sounded almost too convenient to researchers at first, the kind of tidy explanation that invites deep suspicion rather than easy acceptance. Scientists have watched this entire collapse and explosion sequence play out in real time much closer to home, catching bright supernovae flaring suddenly in nearby galaxies and carefully tracking exactly how long each stage of the process takes, from the very first sign of collapse to the final, brilliant explosion and beyond. Every confirmed example matched the same basic timeline closely, reinforcing decades of hard-won confidence in exactly how patient and gradual this particular pathway toward a black hole really tends to be. Extraordinary claims like that one demand extraordinary evidence, and QSO-1, however striking on its own, would need company before anyone could treat a black hole-first universe as anything more than one intriguing possibility worth investigating further. That company arrived sooner than many astronomers expected, hidden inside a galaxy named GNZ 11, sitting roughly 400 million years after the Big Bang. Researchers using the James Webb Space Telescope found a second black hole, behaving in ways that broke the rules almost as dramatically as QSO-1 already had. GNZ 11 itself had already earned a solid reputation among astronomers as one of the most distant, most ancient galaxies ever confirmed anywhere in the observable sky. First spotted years earlier by the Hubble Space Telescope, before Webb ever got the chance to examine it in far greater, sharper detail. Buried at its centre sat a black hole weighing around 6 million times the mass of the Sun, a serious heavyweight in its own right, though notably smaller than the true monster found earlier inside QSO-1. What made GNZ 11's black hole genuinely alarming was not simply its size, but its appetite. This black hole was not sitting quietly, gently sipping material from its surroundings the calm way most ordinary black holes are thought to feed over long, patient stretches of cosmic time. It was gorging itself, pulling in surrounding gas at a rate astronomers rarely see sustained for any meaningful length of time anywhere in the observable universe. Picture the difference between someone eating a normal steady meal spread calmly across a full hour and someone attempting to finish that exact same meal in under 2 minutes flat, gulping down every single bite without pausing once to breathe. That rough comparison captures something of the sheer intensity astronomers were witnessing inside GNZ11, a black hole feeding at a pace that seemed to defy the physical limits normally placed on how fast any black hole can safely consume matter without choking on its own light. Researchers studying this galaxy noted that it was feasting on matter pulled from its surrounding host at a rate strikingly higher than anything considered normal, safe, or sustainable, a detail that immediately caught the attention of theorists who had spent years wondering whether such extreme, rule-bending feeding was even physically possible outside of brief, unstable bursts lasting only moments. If GNZ11's black hole truly had been feeding this aggressively for a meaningful portion of its existence, it offered a genuine, real-world example of exactly the kind of rapid, rule-breaking growth that theorists had speculated about for years without ever managing to catch clear, convincing evidence of it actually happening anywhere in the observable sky. Two separate black holes, discovered in two completely different corners of the ancient sky, both defying long-standing assumptions about how black holes are supposed to grow, though in two very different ways from one another. Unlike QS01, which needed a rare gravitational lens to become visible at all, GNZ11 had already been studied for years before this particular detail came to light, meaning astronomers had a solid, well-established baseline to compare its unusual new behavior against. That made the discovery even harder to wave away as some kind of unusual fluke tied to unfamiliar data, poor calibration, or a poorly understood object nobody had ever bothered studying this closely before now. Confirming exactly how far past the normal limit this feeding truly reached would require a careful look at one of the most fundamental speed limits in all of black hole physics. Every black hole has a natural speed limit on how fast it can safely feed, a boundary astronomers call the Eddington limit, named after the astronomer who first worked out the physics behind it more than a century ago. Here is the basic idea behind that limit, explained as simply as possible for anyone hearing it for the very first time. As a black hole pulls in surrounding gas, that infalling material heats up dramatically from the friction and pressure of the process, glowing brilliantly bright, sometimes bright enough to outshine an entire galaxy of ordinary stars combined into one point of light. That intense brightness produces real outward pressure, a kind of radiation pushing back hard against any new material trying to fall inward at the same time, feed a black hole too aggressively, pushing more matter toward it than that outward radiation pressure can tolerate, and the incoming material effectively gets blown back outward before it can ever actually reach the black hole itself. Picture trying to shove more and more people through a single narrow doorway all at once. Beyond a certain point, the crowd pressure pushing back against that doorway becomes strong enough to actually stop new people from getting through at all, no matter how hard the people behind keep pushing forward. The Eddington limit works in a roughly similar way to that doorway, a natural traffic jam built directly into the physics of feeding itself, capping how quickly any black hole can realistically grow under normal, steady, everyday conditions. For decades, this limit served as a dependable speed check on how fast astronomers should expect any black hole, anywhere in the universe, to grow over time. Sustained, serious violations of that limit were assumed to be exceedingly rare, brief exceptions rather than any kind of reliable, repeatable long-term growth strategy worth building a whole model around. That assumption is exactly what GNZ11 forced astronomers to question directly, since a black hole feeding this consistently, this aggressively, for any real stretch of time would represent precisely the kind of sustained violation the old models insisted should almost never happen at all. The limit is not an arbitrary rule invented to keep the math tidy. It grows directly out of basic physics, the simple balance between gravity pulling material inward and radiation pressure pushing it back out. The same kind of balance that keeps a star itself from collapsing under its own weight while it is still busy burning fuel. Push past that balance briefly, in a short, unstable burst, and most theorists agree it can happen, the way a crowd might briefly surge through a doorway during a sudden panic. Push past it steadily, calmly, for millions of years running instead, and the physics gets far harder to explain using any conventional model built on nearby, well-behaved, ordinary black holes closer to home. That steady, sustained version of the violation is exactly what made GNZ11 worth a second and third careful look before anyone felt confident enough to publish the result publicly. Researchers reran their calculations multiple times over, checking carefully for calibration errors, checking for contamination from nearby objects, checking every reasonable alternative explanation, before finally accepting that the feeding rate really was as extreme as the very first pass-through the raw data had originally suggested. When researchers calculated GNZ11's black hole's feeding rate in careful, painstaking detail, the number that came back sat roughly 5 times higher than that theoretical speed limit was ever supposed to allow, sustained rather than momentary, a serious violation rather than a brief statistical fluke buried in the noise of a single, uncertain measurement. A rate that high, held for any meaningful stretch of time, would let a modest, ordinary stellar mass black hole balloon dramatically in size far faster than the traditional slow, patient model ever predicted, potentially explaining how a black hole this massive managed to exist so early without necessarily requiring the dramatic direct collapse scenario suggested separately by QS01. Picture 2 different explanations for how someone became extremely wealthy at a surprisingly young age. One story involves inheriting a fortune outright, already massive from day one, needing no time at all to build it up gradually. The other involves working at a truly reckless, unsustainable pace, earning and reinvesting money far faster than anyone thought realistically possible, until the total finally catches up to look almost the same from the outside. Both stories can explain the same surprising outcome through completely different paths, and both were now sitting side by side on the table, each backed by real, hard observational evidence pulled from a genuinely different object studied by a different team. One early black hole, the one buried inside QS01, appeared to have started life already massive, skipping the slow climb almost entirely. Another, the one feeding inside GNZ11, appeared to have grown at an almost reckless rule-breaking pace instead, tearing through the Eddington limit again and again without slowing down. Both possibilities pointed toward the exact same broader conclusion, regardless of which specific mechanism turned out to matter more in any individual case. Something about the earliest years of the universe allowed at least some black holes to reach enormous size far faster than anyone had previously believed physically possible, whether by skipping the starting line entirely or by breaking the speed limit again and again along the way. 2 data points, though, however striking each one looked on its own, still left plenty of room for scientific doubt, and doubt of exactly that kind was precisely what the next set of discoveries would soon begin to erode. A single, unusually fed black hole could always be explained away as a brief, temporary spike, caught by pure chance during an unusually active feeding episode that would settle calmly back down to normal again soon afterward. Researchers needed to know whether GNZ11 represented a single passing moment caught by chance, or whether it reflected a genuine ongoing pattern of extreme feeding stretched across a meaningful chunk of its early life so far. Follow-up observations tracking the same object across repeated visits spread out over months and years would eventually help settle that particular question. But for now, the discovery stood as a second, entirely independent crack in a rulebook that had held firm across the field for decades without serious challenge. 2 cracks in the same rulebook, found independently in 2 unrelated corners of the ancient sky, made it considerably harder for any remaining skeptics to simply dismiss either finding as an isolated fluke and quietly move on with business as usual. 2 black holes breaking the rules might still be dismissed as an unlucky coincidence, 2 rare exceptions found purely by chance among thousands of ordinary, well-behaved objects scattered quietly across the deep sky. A team led by researcher Romain Meyer at the University of Geneva went looking for a wider pattern, rather than settling for isolated examples, examining two additional ultra-bright ancient galaxies named Kola 1 and Nepla 4, both dating from roughly 800 million years after the Big Bang, a little later in cosmic history than either QS01 or GNZ11, but still remarkably early by any normal everyday standard. Both objects had already caught astronomers' attention years earlier for their extraordinary brightness, powered by intensely active black holes sitting at their very centres, feeding aggressively enough to outshine most other galaxies from that same distant ancient era by a wide, unmistakable margin. Using detailed spectroscopy gathered by the James Webb Space Telescope, Meyer's team measured the black holes anchoring both systems and compared their mass directly against the mass of the surrounding galaxy in each individual case. The pattern that emerged matched almost precisely what QS01 and GNZ11 had already hinted at separately. In both Kola 1 and Nepla 4, the central black hole again appeared significantly oversized relative to its surrounding galaxy, dramatically out of step with the steady, balanced ratio astronomers had always measured reliably in galaxies closer to our own time. Unlike QS01, which relied on a rare, lucky gravitational lens to become visible at all, Kola 1 and Nepla 4 were bright enough to study without needing any special magnifying assist from a foreground cluster, suggesting that oversized early black holes might not require quite as much cosmic luck to actually find as the QS01 discovery alone had first implied. This was no longer a single strange exception found through an extraordinary stroke of gravitational lensing fortune. This was now a second, entirely independent research group examining two completely different objects using an entirely separate observational method and still landing on the exact same uncomfortable conclusion as the first team had reached before them. Meyer's team published their findings on a preprint server used widely across astrophysics, allowing other researchers to check the analysis quickly rather than waiting months for a slower, formal journal review process to run its full course. That rapid, open sharing mattered because it meant the wider community could scrutinize the claim almost immediately, testing it against their own data and their own methods, rather than simply taking a single team's word for it on faith. The scrutiny held up under real pressure. Both Kola 1 and Nepla 4 kept their oversized black holes under repeated independent examination from other groups, adding genuine weight to a pattern that had, until recently, rested on little more than a pair of unusually striking isolated examples. Researchers outside Meyer's own team ran their own independent versions of the same mass calculation using the same published data, and arrived at figures close enough to the original numbers that nobody could reasonably chalk the result up to a single group's particular choice of method, tool, or underlying assumption about the system. 4 separate objects, spotted using different methods, studied by different teams, scattered across slightly different points deep in cosmic history, all pointing firmly in the same direction. Picture 4 separate witnesses, questioned individually in separate rooms with absolutely no chance to compare notes beforehand, all describing the exact same unusual event in strikingly similar, matching detail. That kind of independent agreement carries far more scientific weight than any single account ever could carry on its own, however compelling that single account might initially appear at first glance. What had started as one strange, lucky discovery behind a fortunate gravitational lens was quickly turning into something that looked less like an accident and more like a genuine, repeating feature of how the earliest black holes in the universe actually came to exist in the first place. Astronomers studying this growing collection of objects began noticing something else worth real, careful attention, that these oversized black holes were not confined to one single, narrow moment in cosmic time, but instead showed up steadily across a meaningful spread of ages, from GNZ11's 400 million years after the Big Bang all the way out to Kola 1 and Nepla 4's later 800 million year mark. A pattern that persists across a spread of time carries far more weight than one can find to a single, narrow snapshot, since a single moment could always be explained away as some kind of unusual, temporary cosmic fluke tied to one specific set of conditions. A pattern stretched across several hundred million years instead starts to look like a genuine, ongoing feature of how the early universe actually worked, not a coincidence limited to one brief chapter. Taken together, these four objects suggested that oversized, early-arriving black holes were not vanishingly rare accidents scattered thinly across the whole observable sky, but rather a real, recurring part of cosmic history during the universe's first billion years, waiting simply for astronomers to build the tools and the survey coverage needed to find still more of them scattered elsewhere across the deep field, images already sitting in the archives. Statisticians who study rare events for a living carry a simple rule of thumb worth remembering here, one that applies just as well to distant black holes as it does to any other unusual pattern hiding in a large data set. Finding one unusual example proves almost nothing on its own. Finding four, spread across different methods and different regions of the sky, starts to look less like chance and more like a real, measurable feature of the underlying population itself. Astronomers were no longer asking whether early oversized black holes could exist at all, a question four separate, independently confirmed objects had already answered clearly enough. They were beginning to ask instead just how common this strange black hole first pathway actually turned out to be across the full, largely unexplored breadth of the early universe. A question that would require dramatically more data, more lens targets, and far more dedicated telescope time before anyone in the field could reasonably offer a confident, well-supported answer to it. Publication of the QS01 results in the journal Nature drew immediate, close attention from astronomers working across the entire field of early universe research, not simply from the small handful of researchers directly involved in the original study itself. Papers describing GNZ11's extreme feeding rate and the oversized black holes anchoring Kola 1 and Kepler 4 followed a similar path soon afterward, circulating quickly through the tightly connected community of scientists, racing to understand exactly what the James Webb Space Telescope had uncovered about the universe's earliest, most formative years. Researchers who had spent entire careers building and carefully refining the traditional, slow build-up model of galaxy formation suddenly found themselves re-examining old assumptions that had gone largely unquestioned for decades on end. Some of that re-examination involved actively searching back through older archived data, checking whether earlier, less detailed observations had perhaps already hinted at the same pattern. Missed, simply because nobody had known to look for it directly at the time those older observations were first taken. Conferences and seminars across the field began dedicating serious time specifically to the question of black hole first galaxy formation, a topic that would have sounded almost fringe or purely speculative only a few years earlier, before Webb had gathered enough evidence to force the conversation firmly into the mainstream of the field. This kind of rapid field-wide shift rarely happens gently or quietly. It tends to arrive as a genuine jolt, unsettling researchers who had built entire careers on one specific version of events, while simultaneously exciting a new generation of scientists eager to explore a genuinely open question, rather than simply confirming an old, settled answer over and over again for decades to come. Textbooks describing galaxy formation, some barely a few years old, suddenly needed asterisks and footnotes acknowledging genuine uncertainty in territory that had recently felt fully settled and entirely complete. None of this meant the old model was entirely wrong from top to bottom. Most galaxies studied closer to our own time still followed the traditional gradual build-up pattern almost perfectly, exactly as decades of careful, patient observation had already shown clearly. What had changed was the growing recognition that the universe's earliest chapter, its first billion years, might have followed an entirely different, far more chaotic set of rules, ones astronomers were only just beginning to properly map out in any real detail. Graduate students entering the field suddenly found themselves choosing thesis topics built directly around this open question, chasing a genuine unknown rather than simply refining an already settled corner of the textbook. Funding agencies took notice as well, directing fresh telescope time and research grants toward exactly this kind of early universe black hole hunting, a clear sign that the shift extended well beyond a handful of excited conference conversations into the actual working priorities of the field going forward. Competition for the telescope's limited observing hours grew noticeably fiercer in the following review cycles, as more and more research teams pivoted their proposals toward hunting for the next QS01-style object hiding somewhere in the deep sky. If black holes really can form directly from collapsing clouds of gas, skipping the long, patient build-up of star formation almost entirely, then the earliest years of the universe must have been a far stranger, far more violent place than most people ever picture when they imagine the quiet, gentle birth of the cosmos. Forming a black hole this way is not simply a matter of having enough raw material sitting around in one place at one time. The gas cloud collapsing directly into a black hole needs to avoid fragmenting into ordinary stars first, a genuinely difficult trick under most normal conditions, since gas clouds almost always break apart into countless smaller clumps long before they can ever collapse together as one single massive unit. Theorists studying this direct collapse process have proposed that intense radiation, likely pouring out from nearby young galaxies already forming and blazing brightly close by, may have played a genuinely crucial role, effectively sterilizing a target gas cloud by preventing it from cooling down efficiently enough to fragment into separate smaller stars the normal expected way it usually would. Picture trying to freeze a large tub of water into one single solid block versus countless tiny individual ice cubes instead. Under most ordinary conditions, water breaks apart into many small separate cubes as it freezes, exactly the way most collapsing gas clouds naturally fragment into many separate smaller stars scattered throughout. Only under very specific, unusual conditions does an entire tub freeze solid as one single, massive block instead, resisting that natural pull toward fragmentation completely. The early universe, still churning with newborn galaxies, fierce radiation, and violently colliding gas clouds, may have occasionally created exactly the right rare conditions needed to force this kind of large-scale, single-block collapse, conditions unlikely to repeat often in the calmer, more settled universe that exists today. If that picture holds up under closer scrutiny, it paints the earliest years of cosmic history as a genuinely chaotic, high-stakes environment, one where massive, pristine gas clouds sometimes skip the normal patient path towards starlight entirely, plunging instead straight into darkness within a remarkably short span of cosmic time. That kind of environment stands in sharp contrast to the calm, orderly, well-behaved universe astronomers observe much closer to home today, where galaxies build up gradually and predictably across billions of patient years without any such drama at all. Some researchers have compared the earliest chapter of cosmic history to a brief, violent gold rush, a narrow window when conditions allowed a handful of gas clouds to strike it enormously rich, almost overnight, before the universe settled into the calmer, steadier rhythm that has defined it ever since. Whether that comparison holds up under closer scrutiny remains an open question, but the basic picture it captures, a short, extreme opportunity available only once, near the very beginning, keeps showing up again and again as researchers dig deeper into exactly what conditions the earliest black holes actually needed to form this way. Simulations built to test the idea on powerful supercomputers have managed to reproduce direct collapse black holes under carefully tuned starting conditions, lending real theoretical support to a picture that started out as little more than an educated guess scribbled on a chalkboard. If a black hole really can form before any meaningful population of stars has had the chance to arrive, then the entire relationship between black holes and their surrounding galaxies deserves a second, far more careful look than astronomers had ever given it before. Rather than treating a black hole as a byproduct of galaxy growth, something that only emerges after enough gas and stars have already assembled themselves into a functioning structure, some researchers now openly wonder whether the reverse sequence might sometimes be closer to the actual truth instead, at least during the universe's earliest, most chaotic chapter. A newly formed black hole, sitting alone in a still mostly empty pocket of space, radiates enormous amounts of energy as it feeds, heating and disturbing the surrounding gas in ways that could plausibly influence or even actively trigger the very first wave of star formation happening nearby it. Under that picture, a galaxy would not simply grow a black hole at its centre over time. It would grow around one instead, shaped from its earliest moments by the gravity and radiation pouring out from a black hole that had already claimed its position first, long before any stars had begun to form nearby at all. Picture a single, blazing campfire lit first in an otherwise pitch-dark, empty field, its heat and light gradually drawing people, activity, and eventually permanent structures toward it over time, rather than a fully built town slowly constructing a single fireplace at its centre, only after every house and street had already been carefully laid out beforehand by planners. That reversed picture carries real, testable consequences for how astronomers should expect early galaxies to actually look and behave under close observation. If black holes sometimes shape their surrounding galaxies, rather than simply growing quietly within them, astronomers might expect to find distinctive patterns in how gas and early stars are actually arranged around these young feeding monsters. Patterns that could look meaningfully different depending on which object, the black hole or the galaxy, genuinely came first in any given system studied closely. QS01's own extreme structure, a black hole dominating nearly 2/3 of the entire system's mass, fits this reversed picture unusually well, offering a real-world example of a system that still looks overwhelmingly black hole first, even hundreds of millions of years after its formation likely began in earnest. Some theorists have started referring to this idea informally as black hole-seeded galaxy formation, a name meant to capture the sense of a galaxy sprouting gradually around a black hole the way a plant grows outward from a single planted seed, rather than the seed appearing only after the plant has already taken root and grown tall on its own. Testing that name properly will require finding early galaxies at several different stages of growth, comparing how much structure is assembled around black holes of similar mass but different ages, essentially building a photo album of galactic childhood spanning hundreds of millions of years rather than relying on a single snapshot. Every model describing how the universe assembled its earlier structures relies on a rough, agreed-upon timeline, a rulebook establishing which events happened first, roughly how long each stage took, and what conditions needed to exist before the next stage could realistically begin unfolding. Stars first, then galaxies, then black holes slowly catching up over hundreds of millions of years, was the backbone of that timeline for decades. Tested repeatedly against every nearby galaxy, astronomers had access to studying in careful, patient detail. QS01, GNZ11, Kola 1 and Nepla 4 together forced a serious, uncomfortable rewrite of at least part of that backbone, pushing the arrival of genuinely massive, dominant black holes far earlier into cosmic history than the old timeline had ever comfortably allowed for anyone to expect. That kind of rewrite does not simply affect one small, isolated corner of astrophysics, tucked away from everything else. It ripples outward, touching nearly every other model built on top of the same basic underlying assumptions. Models describing how the universe's early fog of neutral hydrogen gas eventually cleared away, an era astronomers call reionization, often lean heavily on assumptions about exactly when the first serious sources of intense radiation switched on, sources that include exactly the kind of aggressively feeding black holes now turning up far earlier than expected, models predicting how quickly early galaxies should have grown, how bright they should appear at different distances, and how common massive structures should be at different points in cosmic history all depend, at least partly, on assumptions about black hole growth that no longer look quite as solid as they once did before these discoveries. Astronomers do not casually discard decades of careful, well-tested work overnight simply because a handful of new, striking examples have turned up in recent surveys. Instead, the field moves through a careful, often slow process of revision, testing whether the old timeline still holds in most typical cases while quietly making room for genuine, confirmed exceptions where the evidence clearly demands it, untangling exactly how common each path actually was across the full breadth of the early universe, rather than in just the small handful of unusually lucky, well-studied examples found so far, would take years of additional observation, additional lensed objects, and additional careful patient measurement, work that had, in a very real sense, only just properly begun to unfold. Some cosmologists have started referring to this whole stretch of revision as an active rewriting of the universe's opening chapter, a phrase that captures both the genuine excitement and the real uncertainty running through the field right now, since nobody yet knows exactly how many more pages of that chapter still need to be redrawn before the picture finally settles into something everyone agrees on. Every new confirmed early black hole adds one more data point to that ongoing rewrite, slowly narrowing down which version of the opening chapter actually matches what really happened, rather than simply what earlier generations of astronomers had assumed must be true. Every galaxy astronomers study up close, in careful, exhaustive detail, sits relatively nearby in cosmic terms, simply because distant light takes far too long to arrive for anyone to ever watch a truly ancient galaxy's actual formative years unfold directly and completely from start to finish. That includes our own galaxy, the Milky Way itself. Nobody alive today can look back and watch Sagittarius, a star's own infancy, play out firsthand, the way astronomers managed to catch a fleeting magnified glimpse of QS01's youth, using a lucky combination of timing and gravitational lensing working together. Our galaxy's black hole formed far too long ago, and its earliest formative light left home and scattered in every direction, long before Earth, or the Sun itself, had even finished forming in the first place. That leaves astronomers working with indirect clues instead, piecing together the Milky Way's own deep history, using distant analog galaxies like QS01 as rough stand-ins for events long since hidden from any possible direct observation today. If black holes like the one buried inside QS01 really were common across the early universe, a genuinely open question researchers are still actively working to answer, it raises a genuinely fascinating, if entirely speculative, possibility about our own galactic backyard. Sagittarius. A star, quiet and comparatively modest today, tucked neatly at the centre of a vast orderly spiral, might have started its own life under conditions closer to QS01's chaotic black hole-dominated beginning than to the calm, gradual build-up story usually told about the Milky Way's formation in classrooms. Confirming or ruling out that possibility directly remains essentially impossible using current technology, since the relevant light left our own galactic neighbourhood far too long ago to ever observe firsthand again, no matter how powerful a future telescope might eventually become. What astronomers can do instead is keep building out a fuller, richer catalogue of early black holes and their surrounding galaxies, hoping that a clearer overall pattern eventually emerges from enough individual examples studied carefully across the deep universe over time. If black hole first beginnings turn out to be common rather than rare among galaxies of the Milky Way's general size and type, that would suggest our own galaxy likely followed a similarly extreme dramatic path in its own hidden, unobservable youth, long before any of its current calm, orderly structure had settled fully into place around it. It is a strange thought to sit with, that the quiet, steady black hole anchoring our own galactic centre today, barely noticed by anything orbiting nearby, may have spent its earliest years as exactly the kind of dominant, world-swallowing monster astronomers are only now learning to recognise in the distant ancient light of galaxies like QS01, somewhere in the Milky Way's own deep, unrecoverable past, long before the Sun or Earth existed in any form. Its central black hole may once have dominated its surroundings just as completely, before 400 billion stars and countless clouds of gas eventually grew up around it, and buried that violent early chapter under everything that came after. Little red dots do not simply fade away gently as the universe grows older around them. They vanish almost entirely from the historical record. disappearing from deep field images taken of galaxies less than about 1.5 billion years after the Big Bang. A specific cutoff that shows up again and again across multiple independent surveys conducted by different research teams using different instruments and methods. Whatever these small, intensely red black hole-dominated objects actually turn out to be, they appear to represent a genuinely temporary phase in cosmic history, thriving briefly across the universe's earliest chapters before disappearing almost entirely from view within a remarkably narrow specific window of time. Astronomers have proposed several competing explanations for where exactly they might have gone, though no single answer has yet earned wide, confident agreement across the entire field. One possibility suggests these objects simply grew up, evolving gradually into the larger, more familiar galaxies astronomers already know well from studying the closer, more recent universe. Their once dominant black holes settling down into the same small, modest mass fraction, found anchoring nearly every mature galaxy studied today. Under this picture, little red dots would represent an early, awkward growth phase rather than any kind of permanent, distinct category of object, similar to how a caterpillar eventually transforms completely into a butterfly rather than remaining a caterpillar forever stuck in one form. A second competing possibility points toward increasing dust instead, suggesting these objects might still exist in large numbers even today, simply hidden behind thickening clouds of cosmic dust that block their telltale red glow from ever reaching Earth's telescopes clearly enough to detect and properly identify it all. A third possibility involves changing behaviour rather than genuine disappearance. The idea that these black holes might still exist in large numbers, but eventually settle into calmer, less dramatically fed states that no longer produce the same intense, easily recognisable red glow that first caught astronomers' attention in the earliest deep field images taken. Untangling which explanation, or which combination of explanations, actually accounts for their apparent disappearance will likely require years of additional painstakingly careful observation, tracking individual objects across a much wider range of cosmic ages, rather than simply cataloguing fresh examples from the earliest years alone and stopping there. Some researchers suspect the true answer may involve all three explanations happening together in different proportions, different objects following different paths depending on their exact size, their exact feeding history, and the exact amount of surrounding dust and gas each one happened to be wrapped in its own particular corner of the early universe. Solving this particular mystery matters for more than simple curiosity alone, since knowing exactly how and why little red dots disappear would help astronomers understand whether the black holes hiding inside them survive intact into the galaxies we see today, or whether something about that transition changes them in ways nobody has yet managed to properly trace. Every discovery described so far shares one striking detail worth pausing on directly for a moment. Every single one of these objects, QSO-1, GNZ-11, KOLA-1 and Kepler-4, was found essentially by accident, caught through a fortunate combination of gravitational lensing, careful survey design, and no small amount of genuine scientific luck along the way. None of them were the specific target the James Webb Space Telescope originally set out to find when astronomers first designed its observing programs years before launch even took place. They turned up instead as unexpected bonuses buried inside surveys built for entirely different purposes, hiding quietly in the background of images aimed at completely different scientific questions altogether. That detail carries a genuinely unsettling implication worth sitting with for a moment before moving on. If 4 separate record-breaking black holes have already turned up essentially by accident, without any dedicated, targeted search, specifically designed to find them in the first place, the true number of similar monsters scattered across the early universe could be dramatically higher than anyone has managed to properly catalogue so far, using current surveys and instruments. Most of the deep sky remains entirely unexamined at this level of detail, since gathering the kind of deep, precise data needed to properly measure a black hole's mass. This far back in cosmic history takes enormous amounts of expensive, carefully scheduled telescope time, time that must be shared carefully among thousands of competing research proposals from astronomers working across the entire field worldwide. Only a small handful of patches of sky have received anything close to the intense, detailed scrutiny that first revealed QS01's true nature, hidden behind Pandora's cluster's fortunate gravitational lens sitting directly in front of it. Countless other ancient, overweight black holes may currently be sitting quietly in deep field images already captured and safely stored in astronomical archives, waiting patiently for the right researcher, running the right specific analysis to finally notice them properly one day. Astronomers are already planning new, dedicated observing campaigns specifically designed to hunt for more of these early monsters directly, rather than simply waiting to stumble across the next one by pure chance the way each previous discovery unfolded so far. Whatever they eventually find will help settle one of the biggest open questions left standing in modern astrophysics: whether black holes racing ahead of their galaxies represent a rare, unusual exception, or a genuinely common, ordinary chapter quietly written into the early life of nearly every galaxy in the observable universe, including, perhaps, the very one we call home. Every new deep field image the telescope captures carries the same quiet possibility buried somewhere inside it. Another faint red point of light, another ancient monster waiting patiently in the dark, another chance to learn exactly how strange the true beginning of everything actually was. Somewhere out there, sitting in light that has been travelling toward Earth since almost the dawn of time, an even older, even heavier black hole may already be waiting patiently for the right combination of a fortunate gravitational lens, a curious researcher, and a little more luck to finally reveal it.